Okay, so today we're going to start chapter 31, synthetic polymers. Please make sure you turn in your take-home quiz if you haven't done so already. A couple of announcements. Exam 4 is going to go through section 31.6. That's about 2/3 or so of chapter 31. That represents the sections we will cover today and Monday. And remember that exam is only available Monday and Tuesday. And that's because of the testing center. The testing center, when they cut the number of reading days in the semester from 2 to 1, then the testing center had to close on the last day of classes in order to be ready for exams, to prepare themselves for final exams. And so that's not my fault. We only have 2 days to take this exam. But plan accordingly, and it should be fine. And then our Zoom question and answer session for exam 4 will be held at 10 a.m. tomorrow. I sent the link out by email, so you all should have that Zoom link. So today we're going to talk about chain growth polymers, one of our 2 classes of polymers. And they're made by 3 different methods: radical polymerization, cationic polymerization, and anionic polymerization. So the nice thing about polymers is that the reactions that are used to generate polymers are very simple. And they're all reactions that we've already learned. So we're not going to be learning any new chemistry in this class. We're just going to be seeing in this chapter. We've learned plenty of new chemistry in this class. We're not going to be learning any new chemistry in this chapter. We are simply going to be seeing new applications of reactions that we've already learned. And we're going to see examples of how the structures of these polymers determine their functions. So this is one of my favorite chapters because it is one of the most applicable chapters in the real world. And that's illustrated by this figure right here on the screen. I also like this figure because it shows a mountain biker, and that's one of my favorite hobbies. And this mountain biker is on one of the trails above the Colorado River near Moab. And you can see that their goggles and helmet are made from a polycarbonate polymer called Lexan. Their backpack is made from nylon, another type of polymer. Their tires are made from rubber, which is both a natural and a synthetic polymer. And then their water bottle is made from polyethylene. So, and I'm pretty sure that this person had no idea that the source of all of these products that they're using on a regular basis are synthetic polymers, which originate from organic chemistry and organic reactions. And so most people use, the vast majority of the products that you use on a daily basis are synthetic polymers. And were only created because organic chemists were able to discover those molecules and how to create them. So, and the cool thing, I think another exciting thing about these polymers is based on our knowledge of structure and functional groups, in many cases, we're able to look at a polymer and understand why it is used for the purposes that it is. So, by the end of the chapter, we're going to understand why polyethylene is a very good molecule for water bottles. We're going to understand why rubber is used in rubber bands and tires and why they do different things to rubber to make it useful for the different purposes. So we're going to learn in some cases, not all cases, but in some cases, why the structures of those polymers enable their use. So you can impress your friends and family with all of the cool things you've learned in class and explain to them why their water bottle is made out of polyethylene. Okay? So to start off, there are 2 types of polymers. The first type is, and these are classified based on how they are synthesized. Chain growth polymers are also known as addition polymers. They're called chain growth polymers because we'll start with why they're called addition polymers, actually. They're called addition polymers because they're synthesized by addition reactions. They're called chain growth polymers because they start out with an initiator generating a reactive intermediate from a monomer, and then that reactive intermediate adds to another monomer, generating a new reactive intermediate, which adds to another monomer, and so on and so forth. This happens hundreds or thousands of times. And so the chain, the chain of atoms grows in a stepwise process by the addition of a new monomer to the growing chain. So that's why it's called a chain growth process. The chain is growing in a stepwise process by a monomer adding to the growing chain and then another monomer adding to the growing chain. So it's going to look like this. We have an alkene with a Z group. We have an initiator, and then we just link these chains together. So here I've drawn 3 repeating units inside of these brackets. Sometimes we draw less, but I drew more here for you to make it more clear that when you're doing a chain growth polymerization with an alkene as your monomer, that you end up with whatever the Z group is on every other carbon. Okay. We talked a little bit about polymerization in chapter 15. We talked about the radical type of polymerization back in chapter 15 at the end of Chem 351. And PVC or polyvinyl chloride is an example of a polymer that is generated by radical polymerization where Z is a chlorine. Okay, so vinyl chloride is the monomer. We polymerize that. We have chlorines coming off of every other carbon, and the properties of that molecule are ideal for use in sprinkler pipes and other sorts of things like that. Okay? All right, so these are chain growth polymers. And then our other type of polymers that we have are called step growth polymers or condensation polymers. Okay? So condensation reactions are reactions where 2 molecules come together to form a larger molecule with elimination or loss of a small molecule such as water. Okay? So when we form an ester or we form an amide and water as a byproduct, that would be known as a condensation reaction. So a step growth polymer usually involves 2 different monomers as opposed to a single monomer that's typical for most chain growth polymers. And those monomers in a step growth polymer usually have 2 of the same functional group on each end of the chain. Okay? And so that allows a condensation reaction to occur between the 2 monomers. And then the dimer that you get from that process, the heterodimer that you get from that process, has a reactive functional group on either end. So that allows it to react further, but in 2 directions as opposed to just 1 direction in a chain growth polymerization. So that it's called step growth because the polymer can grow in larger steps than in a chain growth. You can have 2 intermediate sized chains come together to make a large chain. So an example of this is nylon. Nylon is a step growth polymer. There's a couple different ways to make nylon. One of them would involve adipic acid and hexamethylene diamine. So we have 1 monomer with 2 carboxylic acids, 1 monomer with 2 amines. And this is the reaction I told you doesn't work in a typical lab, but sometimes works on industrial scales where you have the ability to heat your reaction to a high enough temperature that you can cause amide bond formation to occur without the need for DCC just by driving off water due to the extreme amount of heat. And so you do that, you make an amide, and you're still going to have an amine on one end and a carboxylic acid on the other, so you can grow these long chains. Nylon 6,6, the name comes from the fact that you have 6 carbons in each of these 2 monomers. Okay, so this is a classical example of a step growth polymer, and then PVC would be a classical example of a chain growth polymer. Any questions? Okay, so a couple of other general facts about polymers that apply to both types of polymers. They're large molecules, and so as you might imagine, they have large molecular weights. Most polymers have molecular weights in the range of 10,000 to 1,000,000 Daltons. Okay, Daltons are the units, grams per mole could also be the units we use for molecular weights. So these are very large molecules. For comparison, most of the simple organic molecules we've talked about in class, which are typically called small molecules to distinguish them from polymers, have molecular weights less than 1,000. Okay, so you can see that polymers are substantially larger and longer chain molecules than our small organic molecules. Another thing is that if you have a sample of a given polymer, the chain lengths are not going to be uniform. It's impossible to make all the chains the same length. You just can't do that. You're going to have a range of chain lengths. Okay? But the chains are so long that the variation in chain lengths is usually relatively small, and so the bulk properties of your polymer material are usually identical. Okay, so even though your polymers are not homogeneous, you're going to have different chain lengths. You're going to have some other small differences in the backbones, as we'll discuss later on today. Because the chains are so long, those differences are negligible. And so the bulk properties are essentially homogeneous of our polymers, even though the sample of polymer is not going to be homogeneous. Any questions? Okay, so let's explore our chain growth polymers in a little more detail. So let's look at our repeating units, how we draw those polymers. On the left here, we have a chain growth polymer, polystyrene. And sometimes I use these little squiggly lines on the board. Other times we're going to use these brackets around a repeating unit of a polymer. And we just put an N there. N is usually a really large number, but we're typically not going to specify what that is. We usually just put an N there. And then this would be a step growth polymer that has two different monomers. In this case, it's a polyester that has a dicarboxylic acid and a dialcohol as the two monomers that are polymerized. So when you have two different monomers, you obviously have to include both of them in your repeating unit. Okay. So one of the skills that is important in understanding polymer chemistry, it's a skill that you almost always see on standardized exams, so it's very likely to show up on the final exam, could very well show up on exam 4 as well, is looking at a repeating unit and determining which monomer or monomers were used to construct that polymer. So let's go ahead and practice this. Okay, we have a chain growth polymer drawn for you on the screen. Go ahead and talk to your neighbors and determine which of the monomers listed was used to synthesize that chain growth polymer. All right, it's getting quiet, so perhaps that means all the answers are in. Let's get those final answers in the next few seconds. Any more? Okay, that looks like we're done. Okay, so which monomer was used? C was used, okay? So if you look at our repeating unit, you see that we have 2 fluorines on every other carbon. So that should narrow it down to C or D, because those are the 2 monomers that have 2 fluorines on every other carbon. Why did you choose C and not D? You surely weren't guessing, because almost all of you chose C, and if you were guessing, then some of you would have chosen D. Trent. Okay, so C is simpler than D. You actually can use a 1,3-diene as a monomer in polymerization. But think back to what we learned in chapter 16 about addition reactions to 1,3-dienes. What remains in the product? Yes, you have an alkene. When you perform an addition of HX to a 1,3-diene, you still have one of the alkenes in the product. And so if you perform a radical polymerization of a diene, you're going to have a double bond in the backbone. Okay, and there's no double bonds here. Okay, very good. All right, so let's take a look at a mechanism for radical polymerization. Before we do that, so chain growth polymerization reactions are going to be chain reactions. And the only chain reactions we've learned about so far in class are radical reactions. Many of the radical reactions, maybe all the radical reactions we learned in class are chain reactions, because those are common in radical chemistry. And they involve an initiation step followed by many, many propagation steps, and then they conclude with a termination step. Okay? So we've only learned about those types of steps, initiation, propagation, and termination, in the context of radical chemistry. But today we're going to learn that you can have chain reactions with other types of intermediates. You can have chain reactions with cationic intermediates and chain reactions with anionic intermediates. But we'll start with the radicals, because those are the ones that we are familiar with. So let's take a look at a mechanism for radical polymerization of styrene. This molecule here has a common name, styrene. When it is polymerized, it generates polystyrene. Polystyrene is the principal component of styrofoam. Okay, so the initiation involves a radical initiator such as a peroxide. A radical initiator has a weak sigma bond that can be cleaved upon addition of heat or light to generate radicals. And once we generate those radicals from the initiator, then that radical is going to add to the alkene, generating a new radical. Now, the radical could add to either of the 2 carbons of the alkene. Why does it add to the carbon, the terminal carbon? Yes, Brady? Yeah, more substituted radicals are more stable. In addition to that, the benzene ring can stabilize that radical by resonance. So you're forming a more stabilized radical. You're also forming a benzylic radical, which is resonance stabilized. So you choose the Z for the particular type of polymerization you're performing, so that the Z group is capable of stabilizing the reactive intermediate. So for radical polymerization, you want a Z group that's capable of stabilizing that radical, such as a benzene ring that can delocalize it. Okay? So when we perform a polymerization reaction, we need a very high concentration of our monomer. We'll have a very low concentration of our initiator and a very high concentration of our monomer. So that once we generate this reactive intermediate, it's going to react with another molecule of our monomer, generating a new resonance stabilized benzylic radical. And that's going to add to another molecule of our monomer over and over again, hundreds or thousands of times. Once the reaction is almost complete, we will have depleted our monomer. So our monomer concentration is going to be low, and the concentration of those long chains is going to be high. Once we get to that point, now it's going to become reasonable for two of those chains to collide with each other, and that would cause a termination process to occur, where we would form a carbon-carbon sigma bond between those benzylic carbons, generating a product. So notice that even though we draw polystyrene just as that repeating unit, which implies that we have a perfectly repeating pattern, we don't have a perfectly repeating pattern of alternating benzene rings. Because at some point in your chain, you're going to have two benzene rings next to each other. And then at the end of your chains, you're going to have these ethers from the initiations. But because the chains are so long, these little imperfections or defects are negligible and they don't impact the bulk properties of your polymer. There is a second way to terminate a polystyrene chain, and it involves reaction of two chains, similar to what we see here, but it involves reaction of them in a different fashion. Okay, so what happens in the alternative termination method is one of our benzylic radicals is going to abstract a hydrogen atom adjacent to a benzylic radical on another polystyrene chain. Okay? And what that does is allow an alkene to form on the radical from where that hydrogen is being abstracted. So in this case, the chains terminate without forming a carbon-carbon bond. And this is a disproportionation process because we've actually reduced this radical, because we've increased the number of carbon-hydrogen bonds. That's one of our definitions of reduction. And then we have oxidized this radical because we have reduced the number of carbon-hydrogen bonds. Okay? So this process introduces additional differences in our chains. So some of our chains are going to terminate with alkenes. Some of them will be looking like this. So we have these minor differences in our polystyrene chains depending on how the process is terminated. We also have these ethers on the ends of the chains due to the initiation process. But because the propagation steps occur hundreds or thousands of times relative to the initiations and the terminations, those variations are insignificant in terms of determining the bulk properties of the polystyrene. Any questions? Okay, so we have here a figure that shows some other monomers that are commonly used to generate polymers via radical polymerization. So we know that the benzene ring and styrene can stabilize the radical intermediate by resonance. We know that radical intermediates, like cationic intermediates, can be stabilized by electron donating groups. You can donate electrons to that half-filled orbital on the radical. And so the chlorine of vinyl chloride, the oxygen of vinyl acetate, those have lone pairs of electrons that are capable of stabilizing those radical intermediates. You can also see that ethylene can be used, where Z is simply a hydrogen atom. Okay? So ethylene, the polymer from ethylene is known as polyethylene. I'm sure you've heard the term polyethylene before because polyethylene is one of the most common polymers in the world. In this case, the radical intermediate that is formed is a primary radical because Z is hydrogen. Primary radicals are our highest energy, least stable radicals, but unlike primary carbocations, they do exist. So whereas you would not be able to polymerize ethylene via cationic chemistry, we can polymerize ethylene via radical chemistry. Okay, any questions? All right, so speaking of polyethylene, there are two forms of polyethylene. We have linear polyethylene, and we have branched polyethylene, okay? And based on the figures, the figure that you see on the screen there, you can see that linear polyethylene molecules would pack more tightly. They would have increased van der Waals forces holding those chains together than branched polyethylene molecules. These would have weaker van der Waals forces, as the presence of those branches would keep those chains from getting as close to each other. Okay? So stronger van der Waals forces in linear polyethylene, weaker van der Waals forces in branched polyethylene. This is fantastic, and this is by design because this enables us to use these two different forms of polyethylene for different purposes. So the linear polyethylene is also known as high-density polyethylene, abbreviated as HDPE. This is very commonly used in water bottles, other beverage bottles. Most of your milk containers are made from high-density polyethylene. Most substances made from plastic will have the abbreviation indicating the polymer that was used to make that material somewhere on the material. So if you have a water bottle and you look on it, on the bottom, you'll usually see either HDPE or you'll see PET. PET is the other common polymer that is used. It is a step growth polymer, so we're going to talk about it on Monday. Okay, but HDPE can be used, and those bottles are hard substances, right? And you would expect them to be hard and firm due to these stronger van der Waals forces. Okay. Our branched polyethylene is also referred to as low-density polyethylene, or LDPE. You're going to have weaker van der Waals forces, so substances made from LDPE are going to be soft and pliable. So LDPE is commonly used for plastic sandwich bags, okay, or Ziploc bags, plastic bags that you put food in. Okay. It can also be used for some types of plastic wrap. Okay. So there's a big difference in your sandwich bags, soft and pliable, you can rip it pretty easily, versus your water bottles, hard, rigid. You pour the material into it, and the substance you pour in takes the shape of the bottle as opposed to vice versa. And that is completely due to the differences in van der Waals forces between the linear chains versus the branch chains. Any questions? All right, so you might wonder, how do we make branched polyethylene? So this slide here shows us the mechanism of branched polyethylene formation. And it is a consequence of the fact that the intermediates, as the polyethylene chain are growing, are primary radicals. Okay? So as the chain grows and you generate these primary radicals, it is thermodynamically favorable for the primary radical to abstract a hydrogen atom from the backbone of another chain, because that will generate a secondary radical. Okay? So your chains are growing, and then every so often they will bump into each other, and the end of one chain will be able to abstract a hydrogen atom from the middle of another chain. And that's thermodynamically favorable, going from a primary radical to a secondary radical. And so now so that terminates one of our chains, but then our secondary radical, we've now opened up a branch point where you can have a branch grow off of that other chain. Okay, and so that secondary radical is going to add to an ethylene molecule, and then this radical is going to add to another ethylene molecule, and you're going to generate those branches. Okay, so yes. Well, they're going to be in the middle somewhere, but yeah, they'll be at random sites in the middle. It's not a controlled process. So you're going to have branches coming off at random sites. But because the chains are so long, the differences in those sites really doesn't impact the bulk properties of the substance. Okay? So after seeing this mechanism, you should recognize that branching is an inevitable consequence of making polyethylene via radical polymerization. So the question should not be how the branches are formed. The question should be, how do you avoid forming the branches? And the answer is, you cannot avoid forming branches if you are using radical polymerization to generate polyethylene. So to form high-density polyethylene, we're going to need a new form, a different form of polymerization, which is one of the subjects that we will get into on Monday in class. Okay? So branching is an inevitable consequence of radical polymerization of polyethylene. So LDPE is the form of polyethylene that is formed via radical polymerization. Any questions? All right, so another type of polymerization is cationic polymerization. And we know that the pi electrons of alkenes are nucleophilic. Of course, we know that cations are electrophilic. We've seen examples of pi electrons of alkenes attacking cations. We actually saw that on Wednesday in class when we were talking about the steroid biosynthesis. We have that crazy polycyclization reaction that occurs when the pi electrons in the styrene oxide are attacking cationic species. Okay? So we can make polymers via generating a cation and then having an alkene attack that cation. Okay? And so we've generated cations from alkenes before by protonating them, and that is how we initiate a cationic polymerization. The protonation is generally performed via a Lewis acid-base complex as opposed to using a Bronsted acid. We've typically seen HCl or HBr, HX typically used to protonate an alkene. You could do that, but apparently, for reasons I'm not clear on, using the Lewis acid-Lewis-base complex is more convenient in industrial polymer synthesis. So boron trifluoride is an outstanding Lewis acid. It's got an empty orbital on the boron. It's got these electronegative fluorines withdrawing electrons from the boron. This is a super good electron pair acceptor. So it coordinates to a Lewis base such as water, generating this complex that has a formal positive charge on the oxygen. Having a formal positive charge on the oxygen makes this thing behave like H3O+, allowing it to transfer its proton to an alkene, generating a new cation. So in this case, because our intermediate is a cation, we would want Z to be an electron donating group that is capable of stabilizing that cation. Okay? And then, because we have a high concentration of our monomer, the new cation reacts with another equivalent of the monomer, and so on and so forth. And then finally, once we have depleted the concentration of the monomer, then our conjugate base, and please notice there should be a negative charge on that boron. Okay, they've drawn it up here. They drew the negative charge on the boron, although we know that negative charge is distributed on the oxygen and the fluorines because those are all much more electronegative atoms than boron. By convention, we draw it on the boron. So that oxygen has a partial negative charge on it, and then it's able to deprotonate adjacent to our carbocation, forming an alkene. So termination in a cationic polymerization involves deprotonation, formation of an alkene. Any questions on this mechanism? So again, these chains, they'll vary in length, but we'll have so many of these propagations relative to the terminations that the bulk properties of these materials will be essentially identical. So, and then another thing to mention is that like with the radical polymerization, where the regiochemistry was dictated by formation of the more stable radical, the regiochemistry of addition to our monomer is dictated by formation of the more stable carbocation. So these additions are going to follow Markovnikov's rule, like other additions to alkenes that we learned back in 351M. Okay, so you're always going to add the cation to the less substituted carbon so that you generate the more substituted carbocation. So this slide here, the upper half of this slide shows two monomers that are commonly used in cationic polymerizations. So 2-methylpropene has got two methyl groups, two Z groups, and that allows us to generate a tertiary carbocation when we add a cation to this monomer. Okay, so tertiary carbocation, more stable form of carbocation. That gives us polyisobutylene, which is going to have two methyl groups on every other carbon. I'm not sure why that makes it an ideal substance for generating balls, but basketballs, kickballs, other sorts of balls that kids will play with on the playground, commonly made from polyisobutylene. And then we saw vinyl acetate on the previous slide as a monomer that can be used in radical polymerization. It can also be used in cationic polymerization. There are some monomers that can be used in both radical and cationic polymerization, and vinyl acetate is one of them. Polyvinyl acetate, which has this ester coming off of every other carbon, is a common component of many paints. Okay, it's not providing the color of those paints; it's providing the consistency of the paint substance. Okay. All right. Any questions about cationic polymerization? So, as you might imagine, if we have an electron withdrawing group as Z, did you have a question? Okay. If you have an electron withdrawing group as Z, that electron withdrawing group would stabilize an anionic intermediate. So a monomer with an electron withdrawing Z group is going to be well suited for an anionic polymerization reaction. And we can see a couple of those here at the bottom of the slide. We can put a nitrile or a cyano group on our alkene. That's going to make it electrophilic, and this is able to stabilize an adjacent anion. We can put a carbonyl group, carbonyl compound such as an ester. So here we have sometimes we have two Z groups. We've got the nitrile and the ester, both able to stabilize an adjacent anion. Polymethyl alpha cyanoacrylate is a common component of superglues. I have no idea why this is really sticky, but if you've ever used superglue, you know that it is. And if you look on superglue, you'll find that it usually says something about cyanoacrylate or polycyanoacrylate as one of its ingredients. So let's take a look at the mechanism of anionic polymerization. And while it's similar to both radical polymerization and cationic polymerization, there is a difference. Okay? So the initiator that we use is going to be a strong nucleophile. So organolithiums are good initiators for anionic polymerization. If a strong nucleophile adds to a double bond conjugated to an electron withdrawing group, you're going to get an anionic intermediate that is stabilized, usually stabilized by resonance with that electron withdrawing group. Okay? So that's how we initiate an anionic polymerization. And if the concentration of our monomer is much higher than the concentration of our initiator, then once we get this anion, it's going to react with another monomer, and so on and so forth, until we start to reduce the concentration of the monomer, and we have very, very long chains. Okay? So a difference between anionic polymerization and our two other forms of polymerization is that an anionic polymerization does not automatically terminate. It is what is referred to as a living polymerization. So you see on the screen that termination occurs via protonation of the anion using water typically. Okay? You don't want water present in the reaction mixture while you're performing your polymerization reaction, because if you do have water in there at the beginning, The water is simply going to protonate your initiator. Right? The reaction between water and the initiator is going to be very rapid, and so you're not going to get started at all. Okay, so you run these reactions, these anionic polymerizations, in the absence of water. And so once you've used up all of your monomer, what you have is this long chain anion here. The reason this is referred to as a living polymerization is that if you were to add more monomer to your reaction vessel, the reaction would keep going. The chains would keep growing. Okay, so the polymer is still alive. It's able to keep growing. So it doesn't terminate until you actually add water, right? So once the chains had reached the desired length, once you'd used up that monomer, then you would add water at the end of the process to kill it, okay? Any questions about living polymerization? Yes? That's a good question. So I know that they have analytical techniques for monitoring radical or polymerization reactions. They have techniques for determining average molecular weights, average chain lengths of these species. I'm just not familiar enough with polymer chemistry to know what those are. So I know they can do it, but I'm not sure how they do it. Okay? All right. So a couple of other types of polymers that we need to learn about. So far, the chain growth polymers we've discussed have all been made using a single monomer. We can have another type of polymer known as a copolymer. So copolymers are going to be made from two different monomers. Of course, most of our step growth polymers are copolymers, but we can also have copolymers of chain growth polymers. And we can refer to copolymers as either alternating. An alternating copolymer is going to have a regular pattern. It's going to be an AB, AB, AB pattern of those two monomers. Or we can have a random copolymer. Okay, random copolymer is going to have some random mixture of A and B. So we have a figure here showing us a couple of common copolymers. These are both chain growth polymers. So if you're making chain growth polymers, they're going to be random. But obviously you can control the ratios of A and B. So if it's 1-to-1, then you're going to have something close to an AB-AB pattern. If it's 1-to-2, then you would have an ABB sort of a pattern for most of the chains. So even with a random copolymer, the chains are long enough that the bulk properties are still going to be essentially homogeneous, even though your chains will be different. Okay, so Saran, as the name suggests, it is commonly, it's the component of Saran wrap. It's kind of like polyvinyl chloride, except it is a copolymer. And so we have a monomer with 1 chlorine and a monomer with 2 chlorines, and that changes the properties. This is one that I can't really explain how or why it changes the properties, but it changes the properties from polyvinyl chloride such that regular PVC only generated by vinyl chloride is used for making sprinkler pipes, whereas Saran is used in Saran wrap. And then here we have a polymer from a diene, a 1,3-diene, copolymerized with styrene. And this is called styrene butadiene rubber. Okay? As we'll learn on Monday, rubber and related polymers to rubber have double bonds in their backbone. And as I mentioned to you earlier in class, when we polymerize, when we use a diene as a monomer, we're going to get an allylic radical as an intermediate. And that allylic radical is going to react at the end of the chain because of there being less steric hindrance when it does so. And so what that does is it embeds the alkene in the backbone of the polymer. So whenever you see alkenes in the backbone of polymers, you know that a diene was used if it is a chain growth polymer. Any questions on our copolymers? Okay, So there's another type of anionic polymerization that we'll talk about, and that involves epoxides as our monomers. So when we're performing anionic polymerization of epoxides, we use hydroxide as our initiator. We'll show you the simplest version first, where we use our simplest epoxide, also known as ethylene oxide, as our monomer. So hydroxide is a strong nucleophile. So we're going to open our epoxide. Generating a new anionic intermediate. If we have a very large concentration of our epoxide monomer, then this new alkoxide is going to add to another molecule. It's going to open another molecule of our epoxide. Okay, and that's going to go on and on and on and on. And then we're going to end up with a long chain molecule. And drawing the repeating units here is challenging, so I'll have to look closely at my notes as I do so. So our repeating unit is going to be made up of 1 oxygen and 2 carbons. So what we'll do is we'll bracket these 2 carbons and this 1 oxygen. And then, of course, we'll terminate by protonating the alkoxide at the end of the chain. Okay. So this substance is known as polyethylene glycol, or PEG. Right? Ethylene glycol is when you have, it's a component of antifreeze, when you have a diol. Ethylene glycol is basically 1,2-ethane diol. And even though you don't use ethylene glycol to polymerize, you use ethylene oxide as the monomer to make polyethylene glycol. It gets its name from the fact that it looks like a polymer of ethylene glycol. So when you use an epoxide as the monomer, you end up with oxygens in the backbone. And your ratio of carbon to oxygen is 2:1. So what do we know about the solubility properties of polyethylene glycol? It's going to be water soluble. Okay, most of our polymers are going to be insoluble in water. You typically don't see plastics dissolving in water, right? They can, some can, but most don't. So polyethylene glycol is used when we need a water soluble polymer. It's used in lotions. It's used in creams. It's used in some shampoos. It's even used in vaccines. I believe some of the COVID vaccines have polyethylene glycol in them. And some people who don't understand chemistry have thought that it has antifreeze in it because antifreeze has ethylene glycol, whereas the vaccines have polyethylene glycol, which, as you know, they have no connection to each other. Okay? But that's some of the disinformation that's been out there. Okay? So, sounds like my battery died on my mic, but we're almost done. We can polymerize substituted epoxides. We'll take our simplest substituted epoxide, where we just have a methyl group coming off, and our strong nucleophile is going to attack the less substituted carbon of that epoxide. Okay. So we would get an intermediate looking like this that could then react with another epoxide, also at the less substituted carbon. And that's going to keep going. Let's see if I left myself enough room to draw this. And we'll draw the repeating unit here. Okay. So this would be a relative of polyethylene glycol that would have methyl branches coming off. It's going to have a 3:1 ratio of carbon to oxygen, so it would be less soluble but you could tune the solubility properties of these polymers based on the type of epoxide that you use as your monomer. Okay? Any questions about anionic polymerization of epoxides? All right, we'll stop there. Please make sure you turn in your take-home quiz if you haven't already. We hope to see you on Saturday, tomorrow morning at 10 on Zoom for our question and answer session for exam 4.